So we come to the earth current chapter. And I would like to start with a very simple question. What is the earth current? Is it current flowing to earth, in earth, from earth? And I found out it's a very difficult definition, so it makes sense to look at this earth current a little bit more in detail. And I would like to start this discussion with a symmetrical three-phase system. Let's assume we have a cable, we have load current flowing. That means the current in each phase is the same. What you sometimes hear is, in a symmetrical system, the sum of all currents is zero. So it's a little bit astonishing in this situation. So if you have, for instance, 100 amp flowing on every conductor, 100 amp plus 100 amp plus 100 amp are 300 amp, not equal zero. So why do we say the sum of the currents is zero? We do that because we have sine waves in a symmetrical system. That means the current IL1 has, for instance, this purple sine wave. The current in phase 2 has the orange sine wave. And in phase 3, we have the gray sine wave. We see here the range in this diagram is 20 milliseconds. That is exactly one period in a 50 Hertz system. The purple sine wave starts at zero with a zero crossing. The orange sine wave has its zero crossing nearly 7 milliseconds later. That is a phase shift of 120 degrees. And the gray curve has its zero crossing another 120 degrees later. That means these three currents in a symmetrical three-phase system have a phase shift of 120 degrees between them. As electrical engineers don't like to draw all the time these sine waves, it makes sense to use another way of indicating that. We draw the sine wave, but basically we only need the information of the amplitude of the sine wave and of the phase shift. And instead of drawing that, we just draw. Oh, sorry, I wanted to indicate one thing. Sum of the currents is zero. You can do that, you can indicate that in this diagram. You see, for instance, if you take this red instant here, you see in this case the gray current is zero. The orange current is minus 100 and something amp, and the purple current is plus 100 and something amps. That means the sum of the three currents in this case is really zero. And you can do that for all other instruments. You always find that the sum of the currents is zero. But let's come back to the drawing with arrows. What we often do in electrical engineering, instead of using these sine waves, we draw arrows. That means the length of the arrow, look at this purple arrow for instance, indicates the amplitude of the sine wave, and the angle of the arrow indicates the phase shift. And in this case, vertical means phase shift zero. Then you see the orange arrow has a phase shift of 120 degrees. And the gray arrow has another phase shift of 120 degrees. So that basically has these three arrows, has basically the same information as the diagram with the sine waves. And what you can see here, if you sum up these three arrows, you also see the sum is zero. The purple one, connect the orange one to that, connect the gray one to that, and you see you end up with zero. That means the interesting thing is in a symmetrical load situation, the sum of the currents is 0, either doing it with these arrows or just summing up the instantaneous values here in the sine waves. That is one thing. Now let's come back to the earth current, and to do that, I would first of all like to draw your attention on the upper part of this slide. This indicates a cable. That means you see here the 3 phases of the cable. On the bottom, the ground. In blue, the conductors. And again, there we have a symmetrical load situation. There is this symmetrical current system flowing in the cable. Now let us assume this cable has a short circuit. There is a problem in the insulation. We have a short circuit here. And what is now going to happen? We will have a current flow on, in this case, phase 3, through phase 3, here to the cable shield, along the cable shield, and then somewhere to ground. Depending on the system situation, part of the current will also flow to the other side. That means you have a very distributed current flow in Earth. Let us look at a similar example for an overhead line that is indicated in the lower part. You see here a few towers. Every tower is grounded with a certain grounding resistance. You see here in blue the 3 phase conductors, and on top is the earth conductor I already mentioned in the beginning. The earth conductor is directly connected to the tower. That means it gives an additional connection of all the towers. And now if we have a short circuit, maybe on the center tower, what is going to happen? You get this strange current flow. That means the current comes from both sides along the line to the short circuit point, and then part of the current flows from here directly into Earth, and another part of the fault current flows along the earth wire into the grounding of other towers on both sides. That means you see here, in case of an earth fault, the earth current is a very distributed thing. There is no one location where you really can measure something, and that makes the earth current sometimes a little bit strange. But let's come back to the question, what is now the earth current in this context? And the earth current is, first of all, just a definition thing. We define the earth current as the negative sum of the 3 phase currents. We just say the earth current is minus IL1 plus IL2 plus IL3. We don't say it's a current flowing anywhere. We say it's just, first of all, an artificial thing with this definition. Unfortunately, it sometimes also has different names. Some people call it ground current. I personally prefer residual current because it doesn't have this strong connection with Earth. But what is now the important fact for protection? The interesting thing for protection is that this earth current is in normal operating states. That means in operating states where we have no fault, this earth current is nearly zero. It's not exactly zero because we have some asymmetries in the system, but it's nearly zero. And in case of an earth fault, this earth current increases. And that means we can use the earth current as a very sensitive criterion to detect phase to ground faults. And always remember, phase to ground faults is the majority of the faults. And phase to ground faults are also those faults which tend to have higher fault resistances No, imagine a tree falls into a distribution overhead line. You can have pretty high fault resistances. That means these are the cases where the fault currents can be pretty low, and it makes sense to have a better opportunity to detect them than we had it up to now when we only looked at the phase currents. If we want to use the earth current for protection, of course, we have to measure it somehow. Of course, theoretically, we can just measure the phase currents and can calculate it internally. What is often done in protection relays is shown here. This is a protection relay connected to the 3 current transformers on the cable or on the overhead line. And what I indicate here are the measuring inputs of the protection relay. We have 1 measuring input per phase. And then these 3 wires are connected here to a star point. And because you bring these 3 wires together, there you have then a location where you have the sum of the 3 currents. And we normally connect this sum of the 3 currents to a 4th measuring input. And this connection is called Holmgreen connection of a protection relay. And I would say that is a standard connection of a protection device. Of course, you could also save 1 measuring input. You could make the whole design a bit cheaper. You could say, as the earth current has this definition, negative sum of the phase currents, it's easy enough just to measure the phase currents and do the computation internally. Well, we have a microprocessor system, there's no problem to sum up the currents. The advantage is if you do this Holmgreen connection, you have a certain amount of redundancy in your data acquisition. That means you can measure the earth current by using this 4th measuring input to measure the sum of the 3 currents. And you can also do the computation internally, and then you can check, is that earth current you measure identical with the earth current you compute? And if you see a significant difference, it is an indication that something is wrong in your data acquisition. That means with this 4th measuring input, you get an additional redundancy in the measurement, and you can, with that, block the system if you detect something. Okay, that was the Holmgreen connection, which is widely used. Important thing here is you have some sensitivity limitations. Sometimes, for instance, in cases where the star point in the system is not grounded, the earth currents can become pretty low. That means you must be very sensitive. If you measure the earth current with this Holmgreen connection, you have the following problem. You measure through current transformers, and these current transformers may have measurement errors. And if all of them have the same measurement error, it's okay. But according to Murphy's law, normally the measurement errors go into the worst direction. You can have the situation that one current transformer, for instance, has a positive measurement error and another one has a negative measurement error. And that means you already get an earth current, even if you have an absolute symmetrical system, you get an earth current just resulting from the measurement errors of the current transformers. And this has to be taken into account. If you want to be more sensitive, there is a possibility, and that is indicated here in this diagram. Then we use a separate CT that is called core balance CT, and that is a CT which physically measures the current of the three phases. That means all three conductors go through the core of this current transformer. And with this installation, you can get a much more sensitive measurements. And for that reason, there are also sensitive measurement inputs available in the relay. So that was the question, how can we measure the earth current? Now let's come back to the question, what are we going to do with the earth current? How can we use the earth current for protection? Remember this picture I showed for the overcurrent protection? You have the normal operation range, you have the range of short circuits, and your setting is somewhere in between. And that means you cannot catch short circuits where the short circuit current is lower than your setting, and your setting must be above the maximum load current. That means you cannot catch short circuits which are, for instance, lower than or close to load current. Now, if we apply the same principle to the earth current, how does it look like? The point here is the green area becomes much smaller, because on the left-hand side, the green area is defined what is the maximum current we see under heavy load condition. If we look at the earth current, even with heavy load, we don't have much earth current. That means we must make up our mind only concerning the question, what is the maximum earth current we see resulting from unsymmetrical operation of the system plus CT errors, but that is much smaller. And that means we can make our setting to distinguish between normal operation and fault much lower than on the left-hand side. And that makes the earth current interesting for protection. That means with that we can detect earth faults where the fault current is lower than the load current. That would not be possible with this just phase measurement I show on the left-hand side. That means nearly all protection relays have, as shown here, a fourth measuring input and at least logic for the earth current. The upper three blue blocks, you have already seen them before. That is the characteristic, the settings for the phase. We add a measuring input for the earth current, Holmgreen connection or internal computation, as I discussed. And then we add here this yellow block, and this yellow block has maybe the same timer settings, but it has a different current setting. It can have a significantly lower current setting to react on earth faults. That means this would be the diagram, the total diagram of an overcurrent relay. That was the chapter about earth currents. I hope it's no longer a secret for you. And the next chapter will just be a very short chapter on primary and secondary quantities in protection.